In the past few decades, microscopy has become a broadly used technique in biological research, where microscopes are now at the forefront of many discoveries. Therefore, optical engineers and scientists invest a lot of time in designing new optical techniques, which would offer a better resolution and the possibility to image deeper in the sample and faster. Among other physical phenomena limiting achieving a better contrast, resolution, or imaging depth, optical aberrations are almost inevitable, whether they come from the optical setup or the sample itself. Although there are a number of different techniques to minimize aberrations, it's almost impossible to fully correct them for every sample at every depth. This is where aberration correction using adaptive optics proves itself useful. Adaptive optics can correct optical aberrations induced by the setup and the sample itself, but it always requires a lot of time to implement it and to use it. MicAO is the first plug-and-play adaptive optics systems, and it was designed for an easy implementation on inverted frame microscopes. It is compatible with 60x and 100x objectives, both CMOS and EMCCD cameras. This video aims to present MicAO device to show how it works, how it can be easily implemented, and what advantages it offers to single molecule localization and spin disk confocal microscopy. The main goal of MicAO is to correct optical aberrations of both the optical setup and the biological samples, and to provide the best point spread function, or PSF. Correction can be done on both emission and excitation path, depending on the setup. This will lead to an increase in both the lateral and axial resolution, an increase in the signal intensity and signal to noise ratio, and a decrease of the phototoxicity. To achieve these improvements, MicAO uses a continuous membrane deformable mirror with 52 electromagnetic actuators, which is calibrated using a high-precision Shack-Harman wavefront sensor. The wavefront sensor is used only during the calibration, at the end of which the closed-loop optimization is performed. This results in almost perfect PSF, which can be further improved using image-based iterative algorithm and aberration depth dependence model. The installation of MicAO unit is straightforward. The first step is to align it with a microscope. It is possible to adjust the height using the feet of MicAO unit and adjust the horizontal tilt by playing with the lateral position of MicAO. Once the optimal position is found, MicAO device is firmly fixed to the optical bench using clamps. Once MicAO is aligned, we calibrate the deformable mirror using a 1 micron fluorescent bead at the surface of the cover slip as a point source to measure the wavefront using the wavefront imager on the camera port of MicAO. During this step, each actuator on the deformable mirror goes through a push-pull cycle, and each corresponding wavefront is recorded. The next step of the calibration aims to correct most of aberrations of the optical setup by performing the closed-loop corrections. In this method, the light from the point source is analyzed using a wavefront sensor still attached to the camera port of the MicAO, and the measured aberrations are corrected by the deformable mirror. For this, we use the same 1 micron fluorescent bead embedded in agarose as a point source. Using this direct measurement of the aberrated wavefront, the deformable mirror changes its shape to get a perfectly flat wavefront. In this example, the flatness of the wavefront based on its RMS value improved from 180 nanometers RMS to 9 nanometers RMS. We have now corrected most of aberration from the scope and the objective lens, but if you use a different sample, aberrations might be slightly different, and if you want to get the best optical resolution or need to obtain more signal, it's very important to correct these tiny residual aberrations. To do so, we now replace the wavefront sensor by the camera and use an iterative image-based algorithm using images of a diffraction-limited bead. By applying a small quantity of specific aberrations, we can measure the quality of the PSF and determine which set of aberrations gives the best PSF. This step can take up to 2 to 3 minutes, but it is very powerful and usually provides the best results you can ever get. In this example, the iterative image-based algorithm improves the signal intensity by 30%, from 9,000 to 12,000 counts. But sometimes, we cannot afford to waste time for aberrations detections, like in spin disk confocal microscopy, while acquiring Z-stacks over a few tenths of microns. To achieve an optimized PSF for each layer in real time, we developed an algorithm that changes the shape of the mirror automatically during the Z-stack acquisition, depending on the current imaging depth. It is based on an experimentally determined model that describes the depth dependency of aberrations. As you can see in this example, we almost doubled the intensity signal of the PSF.